All right, so we're going to start out here on chapter 1, and I'd just like to point out to everybody that as you look at these chapters in your book and most IT books, that most of them are written pretty clearly and usually indicate exactly what you're about to learn on the right beginning of the page, and this book is no different. So the goals here are to learn about computers and programming, uh, making some of your first Python programs, learn the difference between compile time and runtime errors, and finally, all about algorithms, pseudocoding, and a little bit of flowcharting in there as well. The structure of this book, especially if you have an electronic copy of it, the author lists all the extraneous little tidbits that they add to each chapter at the beginning. So if you wanted to jump to specific topics or specific breakout little sessions that they have, you can do that. In addition, this book is also written for various levels of Python programmers. It is really intended as a kind of an intro level book, but it does get pretty advanced pretty quickly. And sometimes we'll offer information for people that just want to know programming, that know business things, that know data analytics or scientific things, or just straight up math. And they have exercises built around that. So they have really rich sets of exercises. I usually keep it pretty basic in this class for you guys because we're mostly web developers and data people, but we will touch upon things that will feed into other areas. But these are all the little special topics that they have here. All of them are hot linked too, so you can go right to those sections. Let's start talking first about what a computer program is and what a computer is for that matter. Because we don't, in the web program, we don't really have like what we call like a fundamental IT course where like the people in the data program you do. So there's a course in the data program called Fundamentals of IT, and we talk about what a computer is, how they work, what software is, how that works, And here we just kind of dive in and kind of skip over that. But I will tell you, it is important to know a little bit about computer hardware as you begin. For most of us, when we're computing, we tend to be using, at least when we get away from our phones, either a Mac or a PC, most likely a PC. Those computer systems are really a collection of hardware. And so whether it's a laptop or a desktop, there's components inside that are similar to every computer system. Every computer system, for example, has a central processing unit or CPU. Every computer system has some sort of RAM or what we call primary storage on the system. Most computer systems have secondary storage, like a hard drive, a flash drive, a DVD drive, or something like that, where you can store things long term. And most systems also have the ability to connect to a network and then connect peripherals so that we can both give input to the machine and get output from the machine. So input devices would be like, for example, a keyboard, a mouse, a microphone, a camera, right? What we type on the keyboard. Output devices could be like the screen, speakers, paper from a printer. Those are all output devices. The thing that's interesting about computer hardware is that computer hardware, when it sits there on its own, is not capable of doing anything until it receives a set of instructions. Now, what we're used to is we buy a computer, we turn it on, Windows is already there. We just start using it. But the people that created Windows did have to create all the programs in order to make it run and allow the programs not only to do whatever they're doing on the screen, but those programs also have to talk to the hardware and make the hardware work correctly, right? So as a computer programmer, it becomes your job to create the set of instructions to make the computer do what it does, however simple or complex that is. And when you start to think about everything your computer does and how frustrated you get with it, keep in mind that some actual human being created what you're seeing on the screen and all the stuff that happens in the background. And sometimes you marvel at the programs that you're using and go, oh my God, this works amazing. Whoever created this is a really smart person. And other times you use programs and like, man, this is really dumb, right? I think I could do better. And you know what? You might be able to. In fact, that's where a lot of niches in programming come in. So a computer program, in short, is a set of instructions that tell the computer what to do. And notice how the terminology. A computer program tells a computer in minute detail the sequence of steps that are needed to fulfill a task. Oh my God, if that doesn't sound like our problem-solving unit, right? Yeah, that's exactly what it is, folks, right? Um, and so the programs that we create are called software ultimately, and the process of creating that software is called programming. So that's kind of the interesting thing. Now here's kind of the fun part of this book. If you have an ebook, by the way, you'll get all these little things that are in chapter, and these are in the printed book too. But in the electronic copy of the book, when they put a question up, you can actually answer the questions, right? So the first question was, the physical computer and peripheral devices are collectively called the, and then you click hardware, and it tells you if you're right or wrong. So let's try the second one. Writing the program for a computer game with motion graphics and sound effects usually requires blank. What's the right answer? All right, what do you guys think? One programmer writing a small number of complex instructions.
Isn't it a team of highly skilled programmers writing a large number of simple instructions?
All right, so Andre is voting for the first one. Mohammed, you said the first one too? Yeah, it says a team of highly skilled programmers writing a large number of simple instructions should be the right answer. And it is. So if I would have put the wrong answer in, it gives you a red X, by the way. But it's okay, you know, Miguel, like you didn't guess the right one, but that's a really common misconception. So the thinking is that when you have a computer game, for example, there's just one geek sitting there writing out every little part of it and thinking of every possible scenario. That's not how it works. Way too complex for one person to handle. A complicated program usually has teams of super skilled people, and then ultimately what they're writing is very, very simple little pieces of code. Combined together, we have something powerful. And this is why we go through the whole pseudocoding thing, because we're breaking problems down into minute detail, because that's what you have to do for a computer program, typically to make it work. But my point in showing you this is wherever they have these screens in the e-version of the book, you can answer the questions. And you know what? I'm just kind of giving you a little heads up. Sometimes these end up on exams, you know. Fair warning. Remember, all your exam questions typically come right from the book. Right. So they start talking about how a computer works, and they get into like the fundamentals of like the CPU. And we think of the CPU often like, so we have a desktop computer here on the instructor station. So a lot of people like, there's the CPU right here, right? And a lot of people call it that. Wrong answer, folks. The CPU is a little chip about this big, maybe the size of like a 50-cent piece, that's like this thin with a ton of really tiny little pins on it that sits on the motherboard. That's the CPU. And technically, even from that size, it's the middle portion that is the computer. That basically is the brain of the computer. Here's what's interesting about that, and you know, normally I do like this big dog and pony show about the history of computing, but you guys can watch the video to get that, so you know. That in the middle of that CPU are literally billions and billions of transistors burned onto super thin silicon wafers. In the old days, when we started building computers, electronic ones, we started with vacuum tubes. And vacuum tubes basically looked like a light bulb, and in some cases were as big as a light bulb and created a whole bunch of heat. When they came up with the first fully electronic computer called ENIAC, that thing had like over 5,000 vacuum tubes, generated as much heat as 5,000 light bulbs. And so they had to have 5 central air conditioning units to cool the room down enough to be able to even stand in there and do any of the work. They came up with this replacement technology called the transistor. I can type it, which looked like this. And so the vacuum tube went from the size of a light bulb down to the size of, I don't know, you know, the head of a pencil, you know, like an eraser on a pencil, tiny. Then they figured out how to do what we call integrated circuits, where they took a bunch of those transistors and they put them together on one silicon wafer with multiple pins. And so this might be like a 16 circuit transistor right here, the one I'm hovering over. And I just want to let you guys know, if you ever formally study computer science or electrical engineering, you do what we call computer architecture design. So you get down to the point where you're designing the circuitry that the computers run on. And that might be for you and might not be for you. But when I studied computer science formally in my undergraduate degree, we had to design a 16-bit processor in our computer architecture class, right? And you know what? If you're thinking about, hey, I'd love to create graphic cards or CPUs or gaming systems, that's the kind of stuff you have to learn to be able to do it. And it really is an electrical engineering task, by the way. So once we got to the integrated circuits, well, that's when things really took off, and we started to just get more and more transistors onto those chips, and that's how we get to these chips. So very often our machines will have chips like this inside, very small little chips. They have pins, hundreds of little pins on the bottom. They plug into sockets on your motherboard. You can see the size of it in this person's hand. And this little area in the middle here literally will have billions of transistors, billions of vacuum tubes. Now we think back to like the first electronic computers like ENIAC, where they had maybe like 5,000 transistors or whatever it was. And now we're walking around with quad-core phones that basically have 4 CPUs and billions of transistors on there, and we're frustrated that like YouTube's not loading fast enough or whatever. Right? So I just kind of want to put things in perspective, right? We've come a long way in a short period of time, but the technology is extremely profound and important and societally transformative. It has been and it continues to be. So I'm not going to do any more than that on there. The other thing that we talked about was primary storage. That's typically our RAM, by the way. Secondary storage is usually your hard disk for most people. And this is what a regular hard disk looks like, by the way. So a lot of people don't know this. So like a typical hard drive on a computer really contains metallic disks on the inside that are magnetically coated. And just like a record player has a read-write head that traverses the disks and reads and writes the information to the rest of the system. Interestingly, when these read-write heads physically contact the disk, right? So normally they don't, right? They hover like less than the width of a human hair above the disk. They just send little electronic pulses and read the information. But if it ever happens to hit the disk, that's what we call a hard drive crash, because the head has crashed into the disk. That's technically a crash. It's not what we think of as a crash. Now, in modern times, we've switched to what we call solid state drives, where we don't have spinning platters, which operate significantly faster. But I think it's pretty interesting to note that the hard drives that we've been using really up until a couple of years ago, and a lot of us still have them in their machines, are really just an extension of the same technology that is a combination of like a cassette tape and a record player. So it's kind of profound that we would use such seemingly primitive technology now that we have SSDs, but SSDs are hugely expensive at first. Another thing that we all do on our computer systems is we do talk to other computers through networks, and I always argue that now we buy a computer, and the first thing we do when we fire it up is we get on the internet, right? Hey, I got a new computer, I'm on Facebook, hey, and in the old days, it wasn't like that, right? Like even like 25 years ago, you'd buy a computer, and if you got like networking on the internet, well, that's really cool. But yeah, you can still do stuff without a computer that's connected. But the modern thinking, it really has become, hey, if we're not connected to the world, what are we doing? All right, moving on. All right. Here's an interesting picture. Remember, we were talking about that first fully electronic computer, actual image of ENIAC, which was the first fully electronic computer that was programmable. Not that computers didn't exist before that. Watch the video for a complete history, actually. But it was in the mid-40s, right at the tail end of World War II, that the Americans were able to build this device. And why did we have the impetus to build these computers? And the answer was pretty simple. We were getting lapped, basically, by the Germans. They had developed electromechanical computers that were way ahead of ours. They had developed jet planes, they had developed rockets, all this advanced technology. And had they maybe strategically waited 6 months or a year before they entered and started World War II, we might all be speaking German right now. I mean, it was that kind of close. What did happen, though, is that Russia, England, and the United States, when we started defeating the Germans in certain ways, and the big defeat really came when the British cracked the Germans' encryption keys using a device called the Enigma Machine. And I think this is kind of an interesting thing because this machine, which looks like a typewriter, was used on all the German ships and remote locations. So the Germans would every morning come up with a new cipher key, and then whatever message they would type into this typewriter, so let's say you type letter A and it would convert it to something else, and then the ship would receive it and then convert it back because they had the same device. And what happened is they were able to, over public airwaves, transmit secret codes and troop maneuvers, ship maneuvers, whatever. And they were kind of in control, folks. They were winning, really, frankly. But what the British did is there was a guy named Alan Turing. Has anybody ever heard of him? And this is what he looked like. Yeah, right on. That's exactly where I'm going. Alan Turing worked for the British government. He was like this mathematical genius, but he worked on an electromechanical computer that was able to eventually crack the code of the Enigma machine. And then the Germans still thought that their messages were going in secret, but the reality was that the British and the Americans were intercepting their messages and deciphering them. And they knew exactly where they were attacking, when, how strong the force was going to be. And then the trick was not to reveal that we knew the code. So sometimes they had to give up a battle, to let them think that they were okay, but then we win the decisive ones. And it was that piece of technology that really ended up kind of winning the war for us. Interestingly, this Enigma machine, there is one on display at the Museum of Science and Industry in Chicago when you go into the submarine exhibit. I don't know if you guys have ever done that, but towards the tail end of World War II, the Americans captured a U-2 submarine and pulled the Enigma machine out, and that's on display there. But it was that device that was giving the Germans the advantage. Alan Turing came up with the machine that defeated it. The movie that McGill's talking about, which is highly recommended just from a computer science standpoint, called The Imitation Game from almost a decade ago now, stars what's his name? Whatever that guy's name is. Yeah, actually, yeah, exactly. It's a really cool movie because it talks about the history of all that, and then it talks about how horrible the British government was to him because he was gay and they ostracized him for it and chemically castrated him. Just absolute horrible story. Considering what he did, he saved the whole Western world from Germany, basically. So I think it's a pretty interesting story, highly recommended. There's also another piece of computer history that ties in with this name, Alan Turing. He conceptualized that there would be a day and age where the computers would become so powerful that we would not be able to distinguish interacting with a computer from interacting with a human. And so he came up with a series of questions called the Turing test, and you may have heard of this, designed to see if artificial intelligence is human or machine. And that was credited all back to him. So the work he did was pretty revolutionary. Here's I think the most fascinating part of that story is what eventually burned the Germans and how they cracked the code is every day they would change their code. So they only had 24 hours to try to crack the code, and then they have to start all over again. But the Germans, being creatures of habit, every transmission ended with a phrase, Heil Hitler. And that's what burned them. Because once they figured out that, that it's like they had so many of the letters already figured out, and then eventually they cracked the code. So fascinating story, great movie to watch, by the way, highly recommended. All right, so now we get to Python. And Python is a language, and I just saw an article about this 2 days ago, that now has, I think, solidly moved into the top 3 of programming languages in terms of demand in industry and practical functionality. The top 2 programming languages, by the way, are the C languages, so C, C++, C Sharp. Those are all kind of a family of languages, and Java. Python is up at the top 2, but it is a different type of language than the others. In a traditional programming language, we do what we call compiling code. So we write our code, the code then is compiled. We look for errors, and then it's converted into what we call bytecode, or machine language, that only the machine can read. And then when you receive it on your computer, it comes in the form of an executable. You run the executable. If you want to see the source code that created it, you can't take a look because it's built into the machine code. You basically have to decompile it. But when you write code in those languages, you write it, it converts to machine code, and then you run it. Python does not work that way. Python is what we call an interpreted language, meaning it is executed on the fly. So we do not create executables in Python. We create a set of instructions that just execute. Not exactly like CSS. CSS is for styling. It's more like JavaScript, though. So when you guys learn JavaScript in web, JavaScript is another one of those languages, not compiled, it is interpreted, which means it directly executes. There's no steps in the middle that turn it into bytecode, which also means you can always see the source code as well, and makes it highly portable and really easy to learn, and it works on basically every platform. The guy who invented the language originally invented it because he was trying to automate server tasks. So he was a server admin, and he would spend his whole life at a command prompt typing in commands for the server, discovering that, hey, every time I add a user to the system, I have to launch the command for adding the user, then I have to update their password, then I have to set their permissions, then I have to create a home directory, then I have to send them an email address. He's like, you know what? All right, that's like 5, 6 separate steps. Why don't I write a little programming language or tool so that I can automate those steps? And so he originally created Python for automating server tasks. And that approach of writing programs is called scripting, by the way. You're scripting out a series of actions. And Python is still very heavily used in that regard. In fact, if you are in the networking, cybersecurity, or computer support specialist programs here, you know, people on the other side of the hall, they also have to take Python, usually not in their first semester, it's like second or third semester for them, to learn how to automate server tasks, because that's one of the tools that's used. Python developed very quickly, though, to the point where not only was it used to do server automation tasks, but actually started to replace traditional programming languages to do some work. All right, the next thing that they go through here in the book in section 1.4 is going through the process of installing the software, which we already did in class, and the links that they provide here are basically the same ones I provided in the program. Once you get everything up and running, you'll notice that they have you write a simple program, which we already did. You guys remember we did that last week, so we're good with that. And they show you how it all works. So that's what this thing's all about. All right. The other thing that's kind of interesting about Python, and I think I demonstrated this right from the get-go, is Python also, because it is not a compiled language, means it can execute commands on the fly. And the example is this. I can go into my console here, and I can just type like a math equation, for example, 2 + 2, and press enter, and it just gives me the output. Right? I didn't write a program. I didn't write code. I just typed in the thing. Or I could do something like print hi. Press enter, and it just does it. Notice I did not write a program. that is the Python interpreter. It interprets the commands and it gives you the output that makes this possible. But it's very telling of how Python operates, because you can do this with Python from what we call the console. Another language that does this that's very popular is JavaScript. So anybody here that's a web student, you will learn how to do the same stuff in JavaScript. And here's kind of like an interesting little thing. So if you have your web browser up and running, you can actually, like, for example, create a tab. You can right click and hit this inspect menu. Right, this is a tool that all web developers learn eventually. And you get all these special tools for web developers, right, that let you break down a page and check the code. But then there's also a console here, which is the JavaScript console. So I can run very much kind of the same thing. I can go 2 + 2, press enter, and get 4. But this is JavaScript doing it, not Python, right? But when you get into that JavaScript class and you start learning a little bit of JavaScript, you're going to see a correlation in how JavaScript and Python operate a lot the same way. These two languages, Python and JavaScript, especially for web developers, have become the primary languages for coding in a lot of different ways. JavaScript much more so than Python. But I like to show that little tidbit. All right, so that's what they're talking about here. When they're talking about interactive mode, it's typing commands at the prompt. All right. Another thing the author suggests is back up your work, right? So when I'm storing my work here in my hard drive on my local machine, seemingly, I'm actually not. I'm actually putting it on my Google Drive. But whatever you guys do for storing your files, you guys need to come up with your own strategy for doing your own backups, whatever that happens to be. My strong recommendation is install Google Drive for desktop on your personal computers, and then whenever you store something on your files here, it goes to your Google Drive automatically, right? Don't even have to worry about backing it up. Real strong suggestion. If you don't like Google Drive, use OneDrive. You don't like OneDrive, use Dropbox. You don't like Dropbox, use Box.
Use them all.
Yeah, I mean, or use them all. Yeah, and that, you know, Miguel, that's actually my strategy. So I run all of those services, and I use different ones for different things. Yeah. You know, so and for me, I can't tell you how many times it's saved my butt, you know, having the stuff out in the cloud. And for web developers, you know, when you're creating content for online, having strong backups of all your work, really, really important, by the way. Let's keep moving forward. They talk about how the Python interpreter works, and you guys can read that on your own. And then we're going to get into coding here in just a second, but I do want to demonstrate a couple of different things. So first is looking at the Hello World program, like we already wrote this last time. And I also want to demonstrate another feature of the electronic version of the book. Notice here they have a little snippet of code that shows a couple lines, you know, so with line numbers. This is a comment, the first line is a comment, and then you have a print command. And notice that there's a run button. So hold on a second. I'm looking at an ebook and I can run the code. Yes, you can. Because Python is an interpreted language, it has the ability to execute within the browser. And I can so any code that's written there, I can run it right inside the ebook. So anytime you see that run button in the book, you can hit that button and run the code. In some cases, you can even change the code and then run it. So it's really cool because you're looking at an example and you can see exactly how it works. Right? And I think that's a really useful tool. One of the reasons I like the electronic version of the book better, just so you guys are aware. So they kind of go through this whole thing here. You guys can read that little section on your own. But a lot of what we're going to be doing here basically is working on different aspects of the print command today. That's our whole point for being here. And so they have examples here that they're going to go through. I think that the examples that we'll do by doing the exercises will be a little bit stronger, and I do want to get to those. All right, so kind of quickly racing through this stuff. And then finally, we get to this section on errors. You know, so, and, you know, sometimes errors are best experienced rather than talked about beforehand. But you will run into problems sometimes when you're running a program and it's not working the way that you intended. What did I do wrong? Right? So then you have to learn how to decipher those messages. Some of those errors are based upon the code that you wrote, right? So for example, this first print command, you say hello world. What's the problem with that command? Yeah, double quotes. It's missing a double quote right here. And the error message for it would look like this. Syntax error, end of line while scanning string literal. Okay, but notice it also puts in a pointer and shows you where it thinks the mistake is. And what it's pointing out is that you're missing a double quote. It would be so much better if it said missing double quote, but that's not what it did, right? So you kind of have to learn how to interpret that. Now that's a coding error, right? That's an error of coding. In other circumstances, you'll write the code correctly, all the syntax is right, but your logic is wrong, and that's a different type of error. For right now, we'll mostly be dealing with coding errors, but sometimes you will write code that's completely correct syntactically, but incorrect logically, right? And that's a different type of error. That's what that's about. And then finally, they get into a section here on problem solving. Hey, sound familiar? They talk about algorithm design. They talk about, the process of pseudocoding. So they demonstrate pseudocoding and they show how to logic your way through it. And then they go into flowcharting a little bit just to kind of give you an idea. But they do that a lot in this book where they give you, for example, a scenario and then how to solve it. And while it's really easy to gloss over that stuff in the book, I do strongly recommend reading it because it is really good if you're brand new to programming to get the process of the problem solving and to see how most computer programs are written. So a lot of them are about like figuring out what math you have to do, what values you have to get, how you're going to make your decisions or whatever, and then put the stuff back on the screen that's correct. All right. Now, I'm going to jump now to the end of the chapter, and I always want to kind of point you here because whenever you do readings, it's not a bad idea to review the summary of what the chapter's about. What were the important takeaways? And you know what, when you're studying for a quiz or an exam or something like that, this is a really helpful section, is the chapter summary that kind of highlights the main topics in the book. Followed by that, you get these interactive screens here, where once again, you're asked questions and you get live responses. Those are pretty fun to go through. So there's a few of those. And they have all these like goofy little practice exercises that you can go through. So if you want like a little bit of practice before you actually write code, there you go. The other thing that they do is they have these review exercises. And the review exercises, I do ask you, if you have the time to go through these, and then all the answers are provided. So these all have the answers provided. Then finally, at the end of every chapter, we'll have the programming exercises. And I want you to notice how the programming exercises have the letter P in front of them. And these are the ones I typically assign. And so if we look at our first set of exercises here, the exercises we need to complete are 1, 2, 6, 9, 11, 12, 14, and 15. And it seems like a lot, but they're all super easy. And we're going to get most of them done before you leave here today. We still have a half hour left. So we're going to start coding. I am going to stop recording right now for the lecture portion because I feel the exercises are pretty well recorded. And so those of you that have to rely on the videos to help you with the exercises, you would be looking at the exercises here. And you see I have them split into 2 portions. And we're going to start working on that. All right, so this video ends here.